the types of forces. So the list of forces whose directions we know. First is weight. Second is pushing contact. Third is pulling contact. And you can always think of that as involving cables. And now we know what to do with that if they go through pulleys too. Fourth is friction. And fifth is the force applied by springs. And we're done talking about those three, so now we're going to start talking about friction. And before I go into that, I want to talk about one mathematical technique we're going to use. So it's like a mathematical approach that we're going to use for all rolling or sliding problems. And it probably makes sense that this is going to be relevant for friction because that's what friction deals with. And so anytime we have a rolling or sliding problem, so like for example, if we have a problem where there's a box here and it's connected to a cart, and they're being pulled up the ramp like this, the approach we're going to take is to choose a coordinate system with the y-axis straight out of the surface. And then you can really think of that as the only requirement. If you draw the y-axis out of the surface, then the x-axis is defined. But this always means that the x-axis is parallel to the surface. So in a problem like the one I drew here, the y-axis would go straight out of the surface, and that means the x-axis has to go this way. Why? So I want to just list out okay, there's a reason for this. So I want to list out the benefits and the drawbacks, and we'll see that the benefits are always going to outweigh the drawbacks. So first, the benefits. The only reason to choose a coordinate system in one specific orientation is that the components of the vectors are going to get simpler. And so that's what we're going to see here in a few cases. The first one is that the acceleration vector, since things that are rolling and sliding can only move along the surface, we're always going to be able to represent this as A0. It's only going to move in the x direction. Notice if we use the normal coordinate system, or usual coordinate system, those would be moving in the fourth quadrant. They'd have an x component and a negative y component, and we'd rather avoid that. So acceleration is simpler. Second, the pushing contact from the surface, the normal force, is always just going to be equal to 0n. It always acts straight out of the surface. So no matter what the problems look like, you know what those, how to represent those, no matter what the angle is or anything like that. Okay. Otherwise, both of those would have x and y components and just be sort of a pain to deal with. Conceptually, it's no harder to deal with, but it would just, you'd have to use cosine and sine to figure out all these things. The third thing, the third benefit is the friction force and that's the next thing we're going to talk about. We're going to use this coordinate system even in problems with no friction, but one of the benefits is when there is friction, it's always an x component only. It could be positive or negative, but it's never going to have a y component. Okay. And then the fourth benefit is any forces parallel to the surface, and that comes up a lot, you know, cables that are parallel to the surface, pushing contacts that are parallel to the surface. They have only x components. All right, there's one drawback, you know, so we have all these benefits. There is one thing that makes it more complicated, but even if you don't have friction, you can see the benefits are heavily leaning towards this being a good idea. But the one drawback is the weight force now gets more complicated. What used to be just 0, negative mg, we never even had to think about it. That always, you know, now we're going to have x and y components because, for example, if you have a coordinate system like, so I'll put it up here. If you have a coordinate system like this, gravity doesn't care what your coordinate system looks like, you know. It doesn't know anything about coordinate systems. It just applies this downward force. So that force is straight down. And so now if you think of this angle theta as being from the positive x-axis all the way around to the weight force, this has a magnitude of mg, then that weight force is going to be mg cosine of theta, mg sine of theta. Okay. And you never, as long as you're calculating your angle all the way from the positive x-axis, you never have to worry about the plus minus sign on your own. The cosine and sine will take care of it. So in this case, let's say that this angle is 20 degrees between, you know, the negative y-axis and the weight force. Then this total angle theta would be 270 to get here, plus another 20, 290. And so the weight force would be mg cosine and sine of 290, and it would put it in the right quadrant for you. Any questions about that conceptually?
Yeah, one question.
Mhm.
Could it be can it have like mg times tangent of theta?
Well,
I'm just thinking.
okay. Tangent, I can't think of how that would come out. But if you don't want to think about it this way, some people feel more comfortable just doing it in terms of SOHCAHTOA, like what quadrant it's in. Figure out the leg over here and the leg here using cosine and sine or whatever. You don't have to do it this way, but this way does always work. And so I think it's a nice, just do everything the same and you're less likely to make mistakes. That's how I think about it. But you don't always have to do it as cosine and sine. There are other ways to do it. All right, so let me do an example. That's the only drawback. Yep. Okay, so let's say that there's an incline that makes an angle of 30 degrees with the horizontal, and there's a cart on the incline. Let's say the cart has a mass of 2 kilograms, and let's say that there's a 5 Newton force pushing the cart up the hill. And we want to know what's the acceleration vector of the cart. Well, the coordinate system we're going to use, because it's rolling or sliding, has the y-axis straight out of the surface. So that's the y-axis, and that means the x-axis is up the ramp. And so the first thing we have to figure out is the weight force. Draw that a little. Okay, weight force. Okay, there's the y-axis, there's the x-axis. And the weight force is straight down. And the magnitude of that weight force is 2 times 9.81, so 19.62. This angle between the negative y-axis and the weight force is always equal to the angle the incline makes with the horizontal. So this angle is 30 degrees. And so the angle theta that we need for the cosine and sine is all the way around from here. Okay, that's theta. So what's that angle theta? 240, that's right. You can think of it as you go from the positive x-axis all the way around to 270 and then backtrack 30. So the weight force is the weight force is 19.62 times cosine of 240, 19.62 times sine of 240. You could also think of this in terms of, make a right triangle with a leg here and a leg here. And, it's in the third quadrant. It's going to have a negative x component and a negative y component. The x component is going to be 19.62 times the sine of 30, and then make that negative. And the y component is going to be 19.62 times the cosine of 30, and make that negative. So that's how, if you want to use SOHCAHTOA, you can do it that way. But coming up with that positive angle, that counterclockwise angle from the x-axis, you just use cosine and sine. You never have to mess with plus or minus. It does everything for you. I think that's probably the way to go in the age of electronic hand calculators and whatnot. Okay, so one of these, that is the x-axis. That comes out to be negative 9.81. Can someone tell me what the negative 16.99? So in that wacky coordinate system, that's the weight force. Okay. It doesn't look like we're used to, but that, like, basically, that has a magnitude of 19.62, and that's in the direction straight down in this off-kilter coordinate system. What's the next step? Better be the next step.
Free body diagram.
Yes, exactly. Okay, so free body diagram of the cart. So we have the weight force. I'm just gonna write that for now as we already figured out the components, but it's just down with a magnitude of 19.62. And now we're just going around the boundary looking for contact. There's a pushing force over here, the magnitude of 5. There's a pushing force from the incline with a magnitude fancy N. Be sure that you're clear to yourself about what's N for normal force and what's N for newtons. And now we can write out Newton's second law. Yeah, I guess that's fine. I mean, I would never take points off, you know. But I would recommend, if you want to do that, put it outside of the body, just so you want to keep the diagram itself pretty uncluttered. We are still doing particle kinetics, and that means that there really are no locations. Everything is happening at a point. And so the only reason I'm separating any of these out at all for now is just to keep it from looking cluttered. So we're lumping both of those two normal forces into one. But yeah, that's a good question. There is really, I mean, I suppose 4 normal forces. We're just lumping them all together. Newton's second law says, in this coordinate system, how do we represent that 5 Newton force? 5, 0. That's just in the positive x direction. The weight force is what we calculated, negative 9.81, negative 16.99. The normal force always just appears as 0n. While you're writing that, you can think about something else. You can take a little mental break. It's not very long, but. And that's all the forces. And all of that is equal to the mass of the body, 2 kilograms, times the acceleration, the way that it always appears. And we've seen this before. Notice that we don't know whether that A value is going to come out positive or negative. We just know that this acceleration has to happen along the x-axis. So we'll write it like that, and then sign will come out in the map. Okay. Well, the y equation would be useful if we wanted to calculate the normal force. We're not asked for it in this case, but you can see negative 16.99 plus n is equal to 0. So n is equal to 16.99 newtons. I've been asked a couple times if the normal force is just always equal to the weight of the object. Often it is, but here's a case where it's not. And then the x equation says 5 minus 9.81 is equal to 2a. So negative 4.81 is equal to 2a. So a is equal to negative 2.405 meters per second squared. And now the acceleration vector is this thing. We just didn't know what that value a was. So now we can, geez. So this thing is the vector a. And so now plug the value in, and you get that the acceleration of the cart is negative 2.4050 in that wacky coordinate system. So is its acceleration up or down the ramp? Down the ramp. Do we know whether it's speeding up or slowing down? We don't. We need one more bit of information in order to know that. We'd have to know which direction it's moving. So it turns out that no matter what the velocity was at this instant, whether it was moving up the ramp at this instant or moving down the ramp at this instant, the acceleration is the same. If it was moving up, our calculation of the acceleration says that it would be slowing down on its way up. If it was moving down, our calculation of acceleration says it would be speeding up. Okay. So until we start dealing with friction, these problems, we won't have to know what direction it's moving at that instant. Once we start dealing with friction, you'll see that we do have to know what direction it's moving. That affects the calculation. Because sort of speaking loosely about it, what friction does is try to slow things down, So it's always, if something's moving this way, the friction force is always trying to fight it to slow it down. Anybody have any questions about this problem? Okay. So now we're going to start talking about friction. And friction is the part of surface contact force parallel to the surface. The other part of the surface contact force is that normal force, and we know that's always perpendicular to the surface. We're going to break friction up into two different types. So there are two types of friction. The first one is static friction. And when an object is not sliding relative to some surface, the static friction is the friction force that prevents sliding. So it keeps sliding from beginning. Second type of friction is kinetic friction. And kinetic friction, when an object is sliding, relative to the surface. Kinetic friction acts to stop the sliding. I mean, it doesn't necessarily achieve that, but that's the direction of the force, is always trying to make it stop. So let's see. So this object, whatever this thing is, it's sitting on the table right now. It's not sliding relative to the table. And so I can't apply a very big force to it without it sliding, but I can apply like a little horizontal force to it. Okay. And without friction, my finger is the only horizontal force acting on it. So Newton's second law, if there was no friction, would say it has to accelerate. Well, it's not accelerating, which means that there's a friction force counteracting that, that's acting opposite of my finger, that has the same magnitude that's keeping it at rest. That's static friction. Okay. Sliding friction, once it starts to move, well, now that it's moving, I'm applying a force to it, right? If that was the only horizontal force acting on it, you would expect it to be accelerating. The velocity should be changing. But when I'm doing this, it's moving with a constant velocity. So again, there has to be some force going in the other direction that has the same magnitude as the force I'm putting into it. And while it's sliding, that's kinetic friction. And we'll deal with those mathematically a little bit differently. Okay, but those are the two types of friction. Yep.
So if there's no other parallel forces on the plane,
Yes, that's exactly right. Yes. That's not true in kinetic friction. It's true in static friction. So like if I push this and like after I let go of it before it stops, the only horizontal force on it is the friction, and that's what makes it slow down and stop. So I'm going to start with static friction. Okay, so how do I want to say this? So when the object is not sliding relative to the surface, static friction acts parallel to the surface as needed to prevent motion, as needed to prevent sliding. Up to a maximum value, a maximum magnitude. And this maximum magnitude is force of friction that's equal to coefficient of static friction, that's the Greek letter mu sub s for static, times the normal force. Okay, so the force of friction is a force that has SI units of newtons. The normal force is a force, so that has units of newtons. So what are the units of that coefficient of friction if you're going from newtons to newtons? It has to be just a plain number. Okay? It can't have any units. Otherwise, I mean, if that had units of newtons, then the force of friction would have to be newton squared. Okay, so this is the coefficient of static friction, and it's unitless. And one thing to notice about this is for the given pair of surfaces, you know, the surfaces of the two objects that are that can possibly slide relative to each other. The maximum value of the force of friction is proportional to how hard the two surfaces are pushed together. Okay, so let me demonstrate what that means. And why I say that mathematically is because you're multiplying this coefficient of friction represents the two surfaces that are in contact. You could look that up for like smooth wood on steel or something, you know, that just represents the two materials. But then you multiply it by the normal force that measures how hard they're pushing against each other to see what the maximum force of friction is. So with this again, remember when I did it before, I can't push it very hard before I exceed the maximum force of static friction and it starts to move. Okay, we saw that. But if I increase the normal force between these, it can generate a lot more static friction before it starts to move. Like in other words, if I press down on it with this hand, that's increasing the normal force between those two. They're pushing a lot harder on each other. And now I can't push it with my finger hard enough to make it start sliding. Okay, it can generate a much bigger static friction force before I finally break past that friction and start it moving. Okay. Any questions about that? Okay, so let me do an example. So let's say we have a box on a horizontal floor. Let's say the mass is 10 kilograms. Doesn't look horizontal, but it's supposed to be. Let's say that we're pushing down on it with a force of 20 newtons, and we're pushing to the right with a force of 40 newtons. At this instant, it's not sliding. And whatever the materials are that the bottom of the box and the surface are made out of, the coefficient of static friction is equal to 0.4. It's almost always between 0 and 1. There are some materials with greater values than 1. Does the box start to slide? So the basic process that we're going to follow is we're going to assume the box doesn't slide. So we're going to assume the acceleration is 0. We're going to calculate the friction force that's required. And then we're going to compare that to the maximum force. If the friction force required is bigger than the maximum, then we know that static friction couldn't hold it and it started to slide. If it's smaller, the force required is within that range of allowable values, then it'll stay at rest. And that'll be the friction force. Any questions about that? Okay, so free body diagram. This is a rolling or a sliding problem, but it's a horizontal surface. So the coordinate system that we use is just the normal coordinate system. The y-axis points straight out. The x-axis is this way. Okay, so the forces, there's a downward force of 10 times 9.81, 98.1. There's a pushing force this way of 40 newtons. There's a pushing force from the ground of N. And then which way is the friction force going to act? The friction force is always parallel to the surface. And so in this case, it has to go in the opposite direction of that 40. It goes opposite the direction that the acceleration would be if there was no friction. You can think about it that way. And that's all the forces. So now we're going to use Newton's second law, and we're going to assume that it stays at rest. What? Oh, I did forget that. Dang it. Yes. Okay.
I have a question. How come like the friction force is like going to left?
Well, so in some problems, it's not super easy to see. But what it's really doing is, imagine there's no friction force. Which direction would the thing accelerate? It would accelerate that way. So friction counteracts that acceleration to keep it at rest. So you can always calculate it that way. But if you have a problem where there's only one horizontal force, it has to be in the opposite of that. Right. The friction force is going to the left in this case. It has to counteract that 40. Okay, so Newton's second law, we're going to assume no acceleration. And we're going to calculate what that friction force would have to be for no acceleration. So 40, 0, plus 0, negative 20, plus 0, negative 98.1, plus 0n, plus negative ff0 is equal to the mass times the acceleration. We're assuming no acceleration, so that's 0. And now we're going to calculate both of these two. The x equation tells us that the force of friction is equal to positive 40 newtons. But in order to calculate the maximum friction, we're going to have to use the normal force. So we need that in this case. So the y equation says N is equal to positive 118.1. Okay, so this is the friction force that's required for it to stay at rest. And now we can calculate maximum force of friction. That's equal to the coefficient, which was given as 0.4, times the normal force, which we calculated. Can someone calculate that? 47.24 newtons. The required FF is less than FF max. So does this slide or not? Stays at rest. Any questions about that?
So you friction max is just what you have to overcome in order to get it to.
Right. That's right.
If there's like no 40 newtons in this case, what the force friction will go to the right. If there's no
well, if there's no horizontal force, remember the real sort of long-winded rule is get rid of the friction force and figure out what the acceleration direction is. The friction force is opposite that. If there's no friction and there's no 40, the thing won't accelerate. So there's no need for any friction force at all. Yep, that's right. Doesn't have to be any. Okay, let's do one more question. Let's say that's part A. Part B, what's the minimum coefficient of static friction so this box stays at rest? Okay, so we know if the coefficient of friction is 0.4, it stays at rest. Presumably it could be a little smaller than that and still stay at rest. You know, maybe 0.35 would work or something. So let's see what the smallest value is. So the free body diagram, we still have all this same stuff. We have the 40, the 20, the weight force, the normal force, and the friction force. Newton's second law, we're going to assume again that it stays at rest. So we have 40, 0, plus 0, negative 20, plus 0, negative 98.1, plus 0n, plus negative FF 0, And we'll assume that it stays at rest. These equations look the same as they did before. So we see that the force of friction required is 40 newtons. And we see that the normal force is 118.1 newtons. But now we're going to say that this friction force, 40, is equal to the maximum static friction force. So this is equal to the mu that we're trying to calculate times 118.1. And so now we can solve for the coefficient of static friction. And what do you get for that? 0.34. And so if the box and the surface are made out of materials that have a static friction force of 0.34 or bigger, then it'll stay at rest. If these two have a coefficient that's smaller than that, say you use the box is wood or something, but the surface is ice, you have a smaller coefficient of friction, then it'll slide. Any questions? Okay, that's all.